Welcome to this session of Materials Engineering. Myself, Anirban Sarkar, Assistant Professor, Department of Mechanical Engineering, JS College of Engineering, Kolani. Welcoming all of you to this session. Today's session, we will discuss about the planar defects of metal. The planar defects or two-dimensional defect that occurs at the surface. This includes external surface such as twins, low angle boundary, high angle boundary, twist, and stacking force. The facial imperfections are arranged differently, divided into two parts, and looks as if one part is a shadow of another when looking at the mirror. That is called the twin boundary. Twins are another example of two-dimensional imperfection, which refers to the area where the reflection of a structure appears through a surface of horizon. It occurs when the material undergoes a plastic deformation or a permanent deformation. In addition, the twin boundaries can be found during the refinement process, whereby the atom itself will redefine position in the annealing twin structure. But this phenomena is only occur with FCC style pipe. So these generally planar defects arise due to the change in the stacking of atom or atomic phases during solidification or mechanical or thermal treatment. The changes may be the orientation or the stacking sequence of the plane, and these are the variances such as like twin boundaries, grain boundaries, etc. Low angle boundaries, etc. So first of all, we'll discuss about that grain boundary. So grain boundaries is generally a planar defect that separates region of different crystalline orientations, that is grains, within a polycrystalline solid. The atoms in the grain boundary will not be in perfect crystalline arrangement. Grain boundaries are usually the result of uneven growth when the solid is crystalline. Grain size varies from 1 micrometer to 1 micron to 1 millimeter. These defects, which separates the grain different orientation from each other and generally seen as an polycrystalline material. And in this figure, it is shown the two-dimensional analogy of the grain boundary, in which the two randomly oriented grains have a region of transition at the grain boundary where the atomic packing is imperfect. Grain boundaries are observed during the solidification of polycrystalline material. Grain boundaries, or that is grain boundary area, or that is actually the length, depends on the grain size of the material and increases with the decrease in grain size and vice versa. Next is tilt boundary. A tilt boundary between two slightly misaligned grains appears as an array of edge dislocation. So in a tilt boundary, it is the edge dislocations are seen, and so that the misalignment grains appears as an array of an edge dislocation. So there are many edge dislocations are present in the tilt boundary. Next is very important, that is called twin boundary. These are the boundaries in the grain at which the atomic arrangement of one side of the boundary is the mirror image of the atom on the other side. The volume of material which has an orientation similar to the mirror image of the matrix orientation is called twins. The mirror is called twinning plane or composition plane. It may form during solidification, deformation, or during plastic deformation and annealing of metals. Next is stacking fault. So before we discuss about that stacking fault, first of all, what is stacking we need to be understand. It is found that lattice structures are described by the stacking of identical planes of atoms one over another in a definite manner. Such as simple cubic and body-centered cubic structures are described by stacking of open planes in a manner that A and AB A respectively. So this stacking indicates that all the planes are stacked in an identical manner and results in a simple cubic structure. AB stacking sequence indicates the second plane is stacked in a different manner to the first. Any one atom from the second plane occupies any one interstitial side of the first plane. Third plane is stacked in a manner identical to the first, and fourth plane is stacked as an identical manner of the second, and so on. This results in a body-centered cubic structure. Another type of structure that is called hexagonal close-packed and face-centered cubic structures are described by stacking of identical close-packed planes one over other. HCP structure is produced by stacking sequence of the type of AB, in which any one atom from the second plane occupies any one interstitial side of the first. Third plane is stacked similar to the first, and the fourth plane similar to the second, and so on. For FCC structure, the stacking sequence is ABC. First two planes are stacked in a similar way to HCP, and third plane, which is designated as a letter C, is stacked in a different manner than the first two. Stacking of the third plane is in such a manner that any one atom from the third plane occupies a common interstitial side of the first two planes. Fourth plane is stacked similar to the first. Fifth plane similar to the second, and sixth plane similar to the third, and so on. Now this stacking fault results from the stacking of one atomic plane out of sequence of other, and lattice on either side of the fault is perfect. The stacking sequence is an ideal FCC crystal is ABC respectively. The stacking fault in this case is due to the missing of any one plane, suppose C planes of atom after their eighth plane. This defect can be regarded as a very thin region of stacking is a basically FCC crystal structure that is now the stacking faults are generally two types as shown here, which is called intrinsic and extrinsic type. Intrinsic fault results one break, where extrinsic fault results in two break in the stacking sequence, as shown in this figure. Stacking faults are easily revealed after etching by a color difference under the optical microscope because the faulty region etches in a different manner than the basic region. Such stacking faults may occur during the crystal growth or may the result from the separation of the two partial dislocations. Now next is called low angle boundary. So what is called low angle boundary? When the orientation of grain differs by only few degrees, a low angle boundary is formed between the two grains. A low angle tilt boundary consists of edge dislocation lying one over another as shown in this figure. Microcracks. Microcracks occur when internal broken bonds creates new surfaces. They are about 10 micron in size and there is a tendency to form on the surface of solids rather than in the bulk. They also form at grains boundaries and other region of disorder. The region across which the bonds are broken is known as separation plane. Microcracks are formed when there is an abrasion or impact with dust particles. They are important in determining how and where a solid may fracture. When a crystal has more than one type of atom, there will be chemical as well as physical disorder in the grain boundaries. Now, volume imperfection, or generally known as three-dimensional imperfection. This volume imperfection or three-dimensional imperfection occurs when a group of imperfection point to by jolt at together. It will happen or pour in contrast. On the other hand, a group of dilute atoms that may merge into a three-dimensional array. The size of volume imperfection may range from a few inches to several centimeters or sometimes larger. Such imperfection will significantly affect the behavior and efficiency of the material. Volume defects, that is generally known as voids, that is the absence of a number of atoms to form internal surface in the crystal. They have similar properties to microcracks because of broken bonds at the surface. Amorphous material and polymers, since they are not just distortion from a perfect crystal structure, microcracks and voids can exist in both crystalline and amorphous solids. Polymers can have partly crystalline region, so may also have all these kind of defects. Next is single crystal deformation, that is deformation of a crystals by slip. So what is its importance? To make the connection between dislocation behavior and yield strength as measured in tension. Consider the deformation in a single crystal. Given an orientation of for single slip, that is resolved shear stress reaches the critical value on one system ahead of all others. Then one obtained a pack of card strain. So let us consider the crystal that is subjected to a tensile load F or P as shown in this figure along the axes. If phi is the angle between the direction of force and a normal to the slip plane, and lambda is the angle between the direction of force and the slip direction, then the area of the slip plane will be A by cos phi, and the force acting in the slip plane in the slip direction will be F cos lambda. The result shear stress in the slip plane and the slip direction, that is tau result, will be F by A cos lambda cos phi, that is sigma t cos phi into cos lambda. So now all this time, as you can see, that lambda, that is the angle between the slip direction and the tensile axis, becomes less and less during the plastic deformation due to the rotation of the slip planes. So rotation of the now at the beginning, if we say that lambda at the beginning is more than 45 degree, and when this lambda decreases, the value of tau resolve as given by this equation, that is sigma t cos lambda into cos phi, that is increases. And it is to be noted that the value of lambda decreases and the value of phi increases and vice versa. Once this is higher than the tau critical, that is it is higher than the critical stress, plastic deformation starts and can be continued even at lower stress. This phenomena is called geometric softening. The materials became soft during plastic deformation. A typical flow curves that is shown in the previous slide, actually, that is the process of geometric softening in the first figure. If the value of lambda at the beginning is less than 45, then as lambda decreases, the value of tau resolve as given by the equation also decreases. For plastic deformation, that is tau resolve should be higher than the tau critical. Therefore, sigma t in this equation, that is tau resolve is equal to sigma t cos lambda became and cos phi, must be increased in such a way that tau resolve is all time higher than the tau critical. for the continuous plastic deformation. That is, continuously increasing stress is necessary for continuous plastic deformation. This phenomena is called geometric hardening. The material becomes hard during plastic deformation. Now, this value of tau resolve is maximum when both lambda and phi are at 45°. Under these conditions, tau resolve is equal to 1/2 the axial tensile strength. The result shear stress is always less than that for any other angles of tau and phi, and tends to become zero at either lambda or phi approaches to 90. Some additional stresses is necessary to continue the plastic deformation than predicted by geometrical hardening phenomena. This is due to the various obstacles to the slipping of planes one over another. The entire phenomena is known as strain or work hardening. And this value, that is sigma t or sigma cos lambda into cos phi, this is known as the Schmidt factor. Now, what is the Schmidt law? It tells that yield stress varies from sample to sample depend on, among several factors, the positions of crystals lattice relative to the loading axis. If the shear stress resolve along the slip direction of the slip plane, that initiates plastic deformation. Yield will begin on the slip system when the shear stress of this system first reaches a critical value, that is critically resolved shear stress, and which is independent of tensile stress or any other normal stress on the lattice. So these are the postulated of the Schmidt law. So we are now concluding in today's session. Thank you for joining this session.